Tonight, we need to talk about cold. Not the cold of a winter morning, not the cold of a frozen lake, not even the cold of Antarctica where temperatures can drop low enough to freeze exposed skin in seconds. We need to talk about a cold so absolute, so complete, so final, that it makes every form of cold you have ever experienced feel like standing next to a fire. The cold of space is not just a temperature, it is a condition of existence. It is what the universe defaults to when nothing else is happening. And by the end of tonight, you are going to understand why the emptiness between the stars is the most hostile environment in the known universe, and why the cold at the edge of everything is stranger and more terrifying than anything you have been told. Here is the first thing that surprises almost everyone. Space is not uniformly cold. The temperature of space depends almost entirely on where you are and what is near you. In the comfortable zone around our sun where Earth orbits, the temperature of sunlight itself is roughly 5,500 degrees Celsius at the solar surface. Stand in full sunlight in space, with no atmosphere to scatter it, no air to conduct it away, and the side of your body facing the sun would be heated to temperatures well above the boiling point of water. The other side, the side facing away from the sun, in shadow, would simultaneously be plunging toward temperatures far below anything on Earth's surface. Space does not average things out, it does not moderate, it does not negotiate. Whatever is happening around you, that is your reality, in full and without compromise. But move away from the sun, move beyond the planets, beyond the outer solar system, beyond the faint gravitational whisper of the Kuiper belt and the Oort cloud. Move into the space between stars, and everything changes. In the vast emptiness between stellar systems, where no star is close enough to warm you, where no radiation is significant enough to matter, the temperature drops to something that has a specific name and a specific number that deserves a moment of genuine silence. Approximately 2.7 Kelvin. 2.7 degrees above absolute zero. Not 2.7 degrees Celsius below freezing. 2.7 degrees above the coldest temperature that physics says is theoretically possible anywhere in the universe. Let's talk about what absolute zero actually means, because this is where the cold of space stops being a simple number and starts being something philosophically astonishing. Temperature, at its most fundamental level, is not a property of matter itself. It is a measurement of motion. Specifically, it is a measurement of how fast the atoms and molecules in a substance are vibrating, rotating, and moving relative to each other. When something is hot, its atoms are moving fast, colliding energetically, vibrating rapidly. When something is cold, its atoms are moving slowly, sluggishly, with less and less kinetic energy. Heat something up and you add energy to its atoms. Cool something down and you remove energy from its atoms. Absolute zero is the point at which you have removed essentially all of that energy. The atoms are no longer vibrating freely. They have reached their lowest possible energy state. They cannot get any colder because there is no more thermal energy to remove. They are, in the most literal sense of the word, as still as physics allows matter to be. Absolute zero is 0 Kelvin, which is minus 273.115 degrees Celsius, or minus 459.67 degrees Fahrenheit. Nothing in the observable universe has ever been measured at exactly absolute zero. But the universe itself, in its vast empty spaces, comes extraordinarily close. That 2.7 Kelvin of background temperature in deep space is not arbitrary. It is not simply the absence of heat, it is the residual warmth of creation itself. 13.8 billion years ago, the universe began in an event of unimaginable heat and energy. In the first fractions of a second after the Big Bang, temperatures exceeded 10 to the power of 32 Kelvin, numbers that have no physical meaning at human scales. As the universe expanded, it cooled. Over billions of years, that primordial heat stretched and thinned and spread across an ever-growing volume of space, and what remains of it today is a faint afterglow of microwave radiation that permeates the entire observable universe equally in every direction. Astronomers call it the cosmic microwave background. Physicists call it one of the most important discoveries in the history of science, and its temperature, measured with extraordinary precision by satellites designed for exactly this purpose, is 2.725 Kelvin. That temperature is the floor, the baseline, the coldest the universe gets in the absence of any local heat source. It is the temperature of space itself, the temperature of the void between galaxies, the temperature of the darkness that surrounds every star and planet and galaxy in existence. And it is profoundly, incomprehensibly cold. To give you a sense of what 2.7 Kelvin actually means for matter, consider what happens to familiar substances at these temperatures. Water freezes at 273 Kelvin. At 2.7 Kelvin, water is not just frozen, it is a rigid, immobile solid where essentially no molecular motion exists beyond quantum-level vibrations. Nitrogen, which makes up 78% of Earth's atmosphere, liquefies at 77 Kelvin and freezes solid at 63 Kelvin. At 2.7 Kelvin, nitrogen is a solid so cold it would not register on most conventional thermometers. Oxygen behaves similarly. Carbon dioxide solidifies at 195 Kelvin at standard pressure. Helium, the most resistant of all elements to becoming liquid or solid, liquefies at just 4.2 Kelvin and solidifies only under extreme pressure. At the 2.7 Kelvin of deep space, even helium is flirting with its liquid state. Everything freezes, everything stops. The universe at its baseline temperature is a place where chemistry as we know it essentially ceases to function, where biological processes are impossible, where even the most fundamental reactions that require molecular motion become so slow as to be effectively non-existent. And this is just the average temperature of the void. There are places in the universe that are colder still. The Boomerang Nebula is a cloud of gas and dust located about 5,000 light-years from Earth in the constellation Centaurus. It is the remnant of a dying star, a shell of material ejected from a red giant in its final stages of life. And the Boomerang Nebula holds a record that, when you think about it carefully, is genuinely staggering. It is the coldest known natural object in the observable universe. Its temperature has been measured at approximately 1 Kelvin, 1 degree above absolute zero. Colder than the cosmic microwave background itself, which means it is somehow colder than the average temperature of the universe. How is this possible? How can anything in the universe be colder than the universe's own background temperature? The answer lies in expansion. As gas expands rapidly into the surrounding space, it cools. This is the same principle that makes an aerosol can feel cold when you spray it. The gas expanding from the dying star in the Boomerang Nebula has been expanding at an extraordinary rate, roughly 164 kilometers per second, for thousands of years. This rapid expansion has cooled the gas below the temperature of the surrounding cosmic microwave background, creating a region that is effectively shielded from the universe's own warmth by the sheer speed of its outward rush. It is a bubble of cold so extreme that the universe's own background radiation cannot warm it fast enough to compensate. 1 Kelvin. In a natural object, in space, right now, 5,000 light-years away. That is how cold the universe can get on its own, without any human assistance. And yet in laboratories on Earth, physicists have managed to cool matter to temperatures far below even this. In experiments designed to study quantum phenomena, scientists have cooled small collections of atoms to temperatures within billionths of a degree of absolute zero. At these temperatures, matter behaves in ways that have no parallel in everyday experience. Atoms stop behaving like individual particles and begin to overlap and merge into a single quantum entity called a Bose-Einstein condensate. In this state, matter is no longer classical. It is fully quantum mechanical. The boundaries between individual atoms blur and dissolve. The collection of atoms behaves as a single coherent wave rather than a collection of separate particles. This state of matter does not exist anywhere naturally in the observable universe. It has only been created in human laboratories, and only by cooling matter to temperatures that make the Boomerang Nebula seem almost warm by comparison. But let's return to space, because the cold of space is not just a curiosity or a number. It is a profound physical reality that shapes everything about how the universe works. And there is something about the nature of cold in space that is deeply counterintuitive, something that confuses almost everyone who thinks about it for the first time. Space is cold. But space also cannot make you cold in the way you might expect. Here is what most people imagine when they think about a human being exposed to the vacuum of space. Instant freezing, the body going rigid and solid within seconds as the cold of space drains all its heat away. This is not what would happen, not even close. Cold, as a physical process, requires a medium through which to transfer. Heat flows from warmer objects to cooler ones through three mechanisms: conduction, convection, and radiation. Conduction is the transfer of heat through direct contact between molecules. Touch a cold piece of metal, and the fast-moving molecules in your warm hand collide with and transfer energy to the slow-moving molecules in the metal. Your hand gets colder, the metal gets warmer. Convection is the transfer of heat through the movement of a fluid or gas. Wind on a cold day removes heat from your body because the moving air carries your body heat away faster than it can be replaced. Both of these mechanisms require matter to work. They require molecules to collide and transfer energy. Space is, to an extraordinary degree of precision, empty. The density of matter in the interstellar medium, the sparse gas and dust between stars, is approximately 1 atom per cubic centimeter. For comparison, the air you are breathing right now contains approximately 27 billion atoms per cubic centimeter. The difference is so vast it is essentially meaningless to say that space contains matter at all, at least for the purposes of heat transfer. There is simply nothing there to conduct your heat away, no molecules to collide with, no fluid to carry your warmth into the void. This means that in the vacuum of space, conduction and convection are both essentially zero. The only mechanism by which a human body in space would lose heat is radiation, and radiation, while real and eventually lethal, is a much slower process than conduction or convection. The human body radiates heat as infrared radiation, and in the vacuum of space, that heat would slowly leak away into the surrounding void. But this would take time, not seconds, not even minutes, hours, potentially, before the cooling became life-threatening from temperature loss alone. The more immediate dangers of space exposure are not freezing but depressurization and oxygen deprivation. Without a pressure suit, the dissolved gases in your blood would begin to bubble out of solution in a process called ebulism, similar to a diver surfacing too quickly. Your lungs would rupture if you tried to hold your breath as the pressure differential tore them apart. You would lose consciousness within about 15 seconds due to oxygen deprivation. Freezing would be the least of your problems. But here is the strange and sobering reality. If you were somehow protected from all of those other hazards, if you were in a pressure suit that maintained your body pressure and supplied oxygen, but the suit provided no thermal insulation whatsoever, you would face a different problem from the one most people expect. In the sunlight, you would overheat. The sun's radiation, unfiltered by atmosphere, would pour energy into you faster than radiation alone could remove it. In shadow, far from any star, you would very slowly cool as your body radiated heat into the void. Not instantly, not dramatically. Slowly, over hours, as the universe's 2.7 Kelvin emptiness absorbed the infrared light your body emits, giving nothing back. This is the true terror of space cold. Not that it kills you instantly, but that it is patient, that it surrounds everything, that it is the default state of the universe, that every source of warmth in the cosmos, every star, every galaxy, every planet with a hot interior, is a temporary anomaly fighting against the baseline coldness that the universe is slowly, inexorably returning to. Because that is the direction things are heading, not just in isolated pockets, everywhere. The entire universe is cooling. When the universe began, it was unimaginably hot. In the first second after the Big Bang, temperatures were so high that matter as we know it could not even exist. Protons and neutrons had not yet condensed from the quark-gluon plasma that filled all of space. The universe was, in a very real sense, pure energy and heat with no structure whatsoever. As it expanded, it cooled. Over the first 3 minutes, it cooled enough for protons and neutrons to form and begin combining into the first atomic nuclei. Over the first 380,000 years, it cooled enough for electrons to join those nuclei and form the first neutral atoms, releasing the light that we now detect as the cosmic microwave background. Over the following hundreds of millions of years, gravity pulled those atoms into the first stars and galaxies, which burned and produced heat and light and the heavier elements that eventually made planets and people possible. But the expansion continues, and as the universe expands, the average temperature continues to fall. The cosmic microwave background, currently at 2.725 Kelvin, will continue to cool. In 1 trillion years, it will be approximately 0003 Kelvin. In 10 trillion years, the last stars will have exhausted their fuel and gone dark. The galaxies that remain will be cold, dark collections of dead stars and black holes, separated by voids of incomprehensible size where the temperature approaches, but never quite reaches, absolute zero. This is the heat death of the universe, the final state toward which all of physics points. Not an explosion or a collapse or a dramatic end, but a slow, patient, inevitable cooling. A universe where all temperature gradients have been equalized, where no hot spot remains hotter than any cold spot, where entropy has reached its maximum value and nothing can ever happen again. A universe at, or as close as physics allows, to absolute zero everywhere. The cold of space is not just the temperature of the void between stars. It is the future of everything. It is where all the energy in the universe is going, slowly and without exception. Every fire that burns, every star that shines, every heartbeat, every thought, every moment of warmth anywhere in the cosmos is a temporary loan against a debt that the universe will eventually collect in full. Zoom out to the largest scales and the universe looks like a brief local rebellion against the cold. A few 100 billion years of stars and light and heat, surrounded on all sides by an eternity of 2.7 Kelvin emptiness, steadily cooling toward a state of perfect stillness that will last, as far as physics can determine, forever. And yet here we are, on a warm rock, orbiting a star, in a universe that is almost entirely frozen. The fact that you are warm, that you are alive, that you exist in a pocket of improbable heat and energy against the overwhelming backdrop of universal cold, is one of the most extraordinary things about your existence. Every atom in your body was forged in the heart of a dying star at millions of degrees. Every bit of warmth you feel comes ultimately from nuclear reactions that have been burning in the sun for 4.5 billion years, pouring energy into the void, fighting the cold. You are, in the most literal sense, a temporary arrangement of star-made matter that has figured out how to feel warm in a universe that is almost entirely frozen. That is not a small thing. That is, as far as we know, one of the rarest things in the observable universe. The cold is everywhere. The warmth is here. And understanding the difference between the two, understanding what that cold really means and how absolute it truly is, makes this small, warm, improbable moment feel like exactly what it is, a miracle of physics, burning quietly against the dark. There is one more thing worth sitting with before we leave this subject, something that scientists rarely say plainly, but that the data makes unavoidable. We tend to think of cold as the absence of something, the absence of heat, the absence of energy, the absence of warmth. And in a narrow technical sense that is true, but in a deeper sense, cold is not an absence at all. Cold is the natural state. Cold is what the universe is. Warmth is what requires an explanation. Warmth is what needs a source, a process, a mechanism to maintain it. The sun burns because of nuclear fusion, a process that will eventually exhaust itself. The Earth is warm at its core because of radioactive decay and the residual heat of its formation, both of which are finite. Every source of heat in the universe is burning through a finite supply of something. Every warm thing is cooling, always, toward the baseline. The cold does not need a source. It does not need a process. It does not need fuel or fusion or decay. It simply is. 2.7 Kelvin everywhere, always, in all directions, the oldest light in the universe slowly fading, the background hum of creation's aftermath, patient and permanent and vast beyond any human ability to truly comprehend. When you look up at a clear night sky and see the stars, you are seeing the exceptions. The rare, temporary, burning anomalies scattered across an ocean of cold that stretches in every direction without end. The darkness between the stars is not nothing. It is 2.7 Kelvin. It is the universe's default. It is what everything was before the stars formed, and what everything will return to long after the last star has burned out and gone dark. The cold is not coming. The cold was always there. We are the ones who arrived late, burning brightly, in the middle of it.